Okay, good morning, everyone. So let's continue with the lectures on jet physics. And so just a brief recap, what we saw was basically the QCD radiation in vacuum, how this builds up to a jet, okay? We still didn't address exactly the properties of angular ordering, but this will be for Friday. Yesterday, we basically understood how the radiation of a single gluon emission would likely to change when in the presence of a quark-gluon plasma. We already discussed exactly how the propagators would change, right? We introduced what we call the Wilson line. And this gives us basically the trajectory of a particle across background fields, assuming that the particle doesn't deviate by the multiple scatterings with the medium. The only thing that will change is basically its color. Okay? And we also introduced the green function, which would be the propagator when we consider, instead of having just the consideration that the particle changes color, we also consider the fact that it might also gain some transverse momentum due to the scatterings with the medium at the same time that its color is rotated. Okay. So today we now move to the next step, which is the amplitude and the cross-section to finally get the spectrum of the single gluon radiation. We already know more or less what we expect, right? The first part of yesterday's lecture was to understand more or less how different was, what kind of expectations we would get from considering formation time arguments, mean free path, and this basically leads us to understand more or less that, yeah, we already know that the radiation is typically soft. These soft emissions are formed earlier with respect to the hard ones, which is kind of opposite what's happened in vacuum, and the angle is typically larger as well. This will contribute to what we see experimentally as jet energy loss. Okay, so today we want to continue in order to have what we call an observable, which be proportional to m squared. And so in order for us to have the m squared, we need basically to have dm times dm conjugate. And this means that before we write the expression, the amplitude, which we still didn't write, right? We only got up to the propagators. But in any case, let me just make a quick detour, because here we'll have already these kinds of objects. Okay, the amplitude of the Wilson line times the complex conjugate of the Wilson line. And one of the things that we still didn't figure out was exactly what to do with these scalar fields. Okay, so of course that's from the point of view of what is happening in the quark-gluon plasma. These scalar fields are not exactly deterministic, right? They will be fluctuations, there will be fluctuations, and each configuration, even though that for a given parton that is crossing the medium, we can consider the configuration of the quark-gluon plasma frozen in some way, configuration from each one configuration to the other, there will be fluctuations, there will be changes in the fields. So this means that we somehow need to average over the whole ensemble of possible quark-gluon plasma configurations. And this is exactly what we want to do. So our central objective, if we want to reach exactly the cross-section or the sketch or the probability of emission of a gluon, we need to consider the object that is a 2-point function, and I will normalize now to the number of colors because we are working under the assumption that is Wilson lines are in the fundamental representation, okay? But of course, this normalization will depend on the color representation that you consider. So if it's a gluon, you need to scale by the respective numbers of degrees of freedom. And what we want is basically, once we have this, we will need to compute the average of this kind of objects. And this is more or less the fundamental object that will describe how the medium correlates the amplitudes and the conjugate amplitudes. This transverse direction, this transverse distance, is basically the distance between the two particles that will form what I call a dipole. Okay? So in this configuration, dipole is just quark, anti-quark particle that would be read out of your cross-section. So before we proceed further, okay, let's imagine that my dipole, in order for us to understand exactly what this object physically, let us consider first the limit of transverse distance equals to 0. Okay? So if I have a transverse distance equals to 0, that means that I have basically my particle and my antiparticle close to each other. Now, I'm assuming that each particle will suffer some sort of color rotation, right? That's what the result of the Wilson line is. But if they are close together, this means that the trajectory of both the particle and the antiparticle will be the same, right? So they go exactly through the same kind of color configuration. So this means that the color rotation over one particle and the antiparticle will be exactly the same. So in this case, they experience the same color rotation. So at the end, there is no color phase between them. So if there is no color phase between them, the interpretation is that simply the medium was not able to decorrelate these particles, okay? And in fact, this SF, this dipole, if I consider now the RT equals to 0, this means that the object that I have is basically the Wilson line evaluated at exactly the same position. So the result is unitary. This is the identity, and then the result is 1. Okay? So when we don't see any kind of medium effect under my dipole, because basically it has 0 dimension, so that the medium cannot really resolve the two particles, okay? This object is 1. This means that when this distance is different from 0, then what I have is basically now already kind of a small shift between them. So this means that the medium feels that this particle and this particle cross are actually different. So there is a phase induced on the system. So in this case, your object is actually smaller than 1. Okay? So we can basically see this as more or less the probability that the particle survives the medium. If it's 1, it survives fully. If it's different than 1, it will have an effect. The medium will be able to have an effect on it. This will become a little bit more clear if we now try to really calculate exactly what is this object. Okay? Let's do like this. And what we want now is basically to perform these medium averages. For that, I need to try to understand exactly what I'm aiming for. So let's consider a slab of medium. And now I have basically a high energy particle propagating through it. Okay? As defined, this goes x plus direction. Now, because we are in the limits of very high energies, okay, we always assume that, yeah, the medium is kind of frozen, and we are only sensitive to each kind of slab, longitudinal slab in the medium, from one point to the other. What this means is that at each point, okay, at this coordinate, x prime plus, the particle will see basically the medium's fields that are along this sheet. When it goes one step further, it will interact with the subsequent fields. But we will not take into account any kind of correlations between the fields at one given longitudinal position and the following ones. So we can only interact with one longitudinal position at a time. And so what we want is basically to perform an average along exactly this plane. So the of not longitudinal corrections, of not longitudinal correlations. In our case, because the quark-gluon plasma is more or less already thermalized, it's not, I mean, you could go further, but this would amount to take corrections of the longitudinal momentum of the particle. So, but for instance, for a CGC calculation, no, this cannot be done. This is actually one of the problems to extend this before the quark-gluon plasma phase. So I will now consider this slab to be at a position xn plus, and the fields to be spread across the transverse plane. Okay? So this means that my fields now are localized at x plus, can be written as a sum of the Fourier transform of your potential in momentum space okay? And so if I now want to calculate basically the correlation between two Wilson lines, I will need at some point to calculate the two-point function of these two fields, okay? This is yet another assumption, which is to say we are only going towards the first n-point correlation function that we are allowed, okay? So this means that we are bounded just to two-point correlation functions. And this you can easily also get that because of our assumption of assuming that the fields are uncorrelated in time, this means that we always have this delta function, color conservation. Yes? See, yes. So A and B are the color indices of the field, and minus is because it's the only component of your field that survives, right? In the, I just erased. But the Wilson line is just the product of a several components minus of your fields, A minus, across the longitudinal direction. Okay. This one, no. The where we introduce here already the density of scattering centers. Okay. And so if I now expand basically the results of these Wilson lines, I usually now will put just the average in front of the trace, just again to minimize the heaviness of this kind of notation. And now, I mean, the Wilson line is an exponential, so let's expand this in the fields. So what we'll have is basically now the first term, which is the unitary. Then I will have the linear terms in the A. Of course, that if I perform the average over one field, the result of this expectation is 0, okay, because I basically I average over one single field, so there is no effect. But when I now consider two-point functions, so two fields, the correlation of two fields, I will get exactly the results that we have there. And of course, I will have higher terms, okay? So I will have the 3-point function, 4-point function, 5-point function, etc., etc., etc. Okay, so yeah. So one of the fields, if you now average basically over the longitudinal components, you can see that this is 0 because it's just the average over the field itself. So you're not going to have an effect. Okay. Exactly, exactly. Okay, so the only thing that you will have is when you introduce some sort of distance between the fields. Then you have this interference. And this interference comes from the fact that now it's more easy to understand exactly what we wanted to say with that object being 1 or 0 that the medium cannot resolve. Because if you look now for this, you have these terms here, which are unitarity and don't have any kind of contribution from a phase. And this unitarity comes, if you do this carefully, side by side, you will see that these terms correspond to what we call the contact terms. And at this point, it's easy to draw because you only have two medium insertions, actually. You only have one. Okay. The second one is actually when you have the medium able to resolve the dipole. So these ones are related to this, and this one is related to that. This one doesn't have any medium, so there is no medium insertions. And now you can see that basically the result is to expand this order by order in the fields. Okay? We will not do that, but you could. Okay? So the resolution of your dipole comes from this term. This is the only term responsible for exactly having a net effect that is not exactly zero. Okay, if we would continue this endlessly, you would reach basically a series that you now can basically resum back. And because we are only considering the 2-point correlation function, so we are discarding higher order correlations of the fields, okay? You would get basically what we would again reinterpret as an exponential. So if I now resum over all, and here there is an object that I will call the dipole cross-section. And this dipole cross-section now is given by the coupling and the Fourier transform of your potential in momentum space times this difference of phases. Okay, and that's why we call now this a cross-section. So this is the probability of interaction of the dipole with my medium, and as you can see, if x and y are 0, so if my dipole has 0 transverse size, this dipole cross-section is 0, so it doesn't interact. That's why this object is defined as 1, which is the probability of survival to the medium. Okay? So if it doesn't interact, it survives. That's how this goes. And all the information of your medium now, because so far we simply kind of hand-waving the arguments for the kind of style of medium that you would like to include, now it's encoded in this potential. And for instance, one of the things that you can use is basically say, okay, let's do a Yukawa type potential, so a Coulomb but screened. So this would be one of the examples. The Dubai screened potential with mass mu. Of course, now you could include, for instance, hard thermal loop corrections. Okay, you can be as fancy as you want on this part. Okay? This would basically will be the building block in which you plug in all the information of your medium, because all the others comes from our own assumptions regarding the medium. Okay? Yeah. Yes. So in principle, what you could, or you, So this assumption comes from the fact that you consider that your evolution of your quark-gluon plasma is slower than the propagation time of your particle across the medium. But of course, that in any case, when you consider, in fact, a process of radiation, the process of radiation now enters in the scale of exactly the formation time for a new emission. And this we already know that is on the scale of the quark-gluon plasma evolution. So what we usually consider is that these averages, although they are uncorrelated in time, they actually are performed kind of semi-local, in the sense that we kind of have the averages performed independently across the propagation of your particle. And this gives you a first correction exactly for these longitudinal corrections. So during the propagation, you assume that, yes, it's static, but as soon as your number of emitters in the medium will evolve, you need to, let's say, update the information on your medium configurations. Mm-hmm. So it's gauge dependent, but in any case, for high energy, you can check that the result is invariant. So that's our assumption, because don't forget that at the beginning we actually fix the gauge based on the fact that we are at a high energy and you are always propagating along the light cone direction. But it's something that you need to consider if you want to go for lower and lower and lower energy. That's will fit. Sorry? So these results is for high energy is fine. There's no problem with this. Okay. So, but in any case, all these assumptions behind even the propagation of Wilson lines are only valid as long as you are at a very high energy, because otherwise your non-aconal correction starts to matter, and you start to have corrections of 1 over the longitudinal direction, or the longitudinal momentum, sorry. And that's where you have to now be more careful and revisit your calculation. Okay. These, of course, are refinements that people are right now targeting. So one of the things, for instance, is here we are indeed considering that the medium is kind of static in a sense. So we are considering just the evolution in given local stuff. But for instance, this might not be the case. This is true for a central-center collision, but this might not be the case, for instance, for a peripheral collision, where we know that the medium now starts to have a flow. So we need to take into account these gradient corrections of your flow into the calculation, for instance. So you can introduce this. Okay. Okay, so any more questions regarding this? Now, if we go back now to the amplitude, okay. If you recall the result of considering like multiple medium insertions, which was the setup in which we derived basically the Wilson line, we got something like this. Okay, with some prefactors, the longitudinal momentum that was there also, okay? But I'm just putting now the transverse information. And this basically gives us the probability, or it would give the probability, if we square it, to basically have the particle shifting from P to P prime, right? So let me just simplify this because it's easier to understand now what's happening. And let me rephrase this as the probability of a particle that initially is at momentum 0, let's say, and just gain some kick. So this would be like the matrix element, the probability, would be given exactly by this object. Okay. And this is what we call the broadening that your particle can acquire in the transverse direction. Yes? The exponential is, wait. Was this the problem, right? Yes. Okay. So now, if I look at this, we know that this dipole correlation function was exactly the trace of these two Wilson lines. And this means that now I can simply, and that's why actually we call this the broadening, I can simply reinterpret this object, and now I shifted from PT to KT just because we usually classify the momentum of the gluon exactly as K-perp. But as you can see, the K-perp, or let's call it the conjugate momentum of your transverse directions, or your transverse size of your dipole, is exactly the broadening of your system. Okay? So the transverse momentum is conjugate to the transverse separation. Okay. And why do we interpret this as exactly the broadening of your system? Because now if this dipole correlation falls very fastly, and don't forget that when this SCF is smaller than 1, this means that the particle is starting to be affected by the medium, right? Because the dipole cross-section is positive. So this comes smaller than 1. This means that this conjugate variable is actually larger, right? You have a larger spread in your conjugate variable. And so this means that it's more likely that the particle will acquire a transverse momentum when we go to momentum space. Okay? And this gives you exactly the property of diffusion. Because don't forget that this arc perp, when it's different from 0, you are considering different shifts in the transverse plane between your particle and your antiparticle. So if the medium is able to decorrelate these two, this will create some sort of smearing between the two that you will see in the conjugate momentum. So when we go from coordinate space to position space, from coordinate space to momentum space, your momentum configuration now, instead of having a very precise momentum, no, it's broadened. Okay, you have like a larger distribution in the momentum. And that's why we interpret this object as the broadening of your system, which is kind of funny because up to here, we didn't even consider broadening in our particles, right? Because our particles were following straight lines. So we don't consider explicit Brownian motion in the transverse plane. However, it arises from the statistical process or the statistical average across your medium configurations. Okay? So even though they are local, because you average over the transverse positions and you consider the smearing of your system, you get, nonetheless, a statistical broadening of your system. Okay? And so with that interpretation, we go back to our main object. Okay. So hopefully by now, we already understood exactly what is the physical meaning of this object, why there is a term that we call dipole cross-section, and what this actually represents in terms of the particle. Now we need to solve this, okay? And solving exactly these two-point correlation functions is not exactly the challenge. The challenge will be when we go back to the amplitudes, okay? Don't forget that we have the propagator, at least for one of the particles, as a green function. This green function amounts to evaluate the path integral, okay? And as you can imagine, there are not many cases in which we can solve analytically path integrals, but for a couple of situations, okay? So even though there has been some evolution to actually understand or find ways to solve this exactly, okay, let me just give you what has been the state of the art in the previous, I don't know, maybe 5-10 years ago. And this was to calculate exactly this kind of dipole correlations or dipole objects in some limiting cases. And there are basically two limiting cases in which we can solve this analytically without recurring to any kind of more fancy methods. The first one is to consider that my dipole has kind of a small transverse size. Okay? And, okay, you can ask, but why small r's? What exactly are we considering? What we are considering when we say that there is a small r expansion, we are considering the fact that your dipole has a very small transverse resolution. So the medium will try to interact with these particles, but sometimes it will be able to resolve them, sometimes it will not, right? So we don't expect we have like sort of multiple interactions, but the result of these multiple interactions will be kind of soft momentum exchanges. And so usually this kind of approximation reflects a physical situation in which you have, many soft scatterings characterized by small momentum transfers So momentum exchange with the medium is much smaller than exactly the transverse direction of your particle. And the situation that you have is actually kind of similar of what we depicted with the green function. So you can consider just, okay, at each step it receives a small kick, and because these kicks, of course, are not exactly building momentum in exactly the same direction, you kind of have some sort of random trajectory, okay, across this. This is what we call the harmonic oscillator approximation. And as the name implies, this means that the only term that we'll be saving out of that potential will be the quadratic one. Because at the end, we will have a quadratic potential that will resemble exactly the harmonic oscillator potential. Okay, so that's why this one, we know how to solve it. Okay, and this will be the one that I will explain in a little bit more detail, because it allows us again to connect with exactly the parameter that we introduced last lecture, which was the jet transport coefficient, Q hat. And here, you can see very nicely how this exactly appears in this kind of formalism. But this is just an approximation, okay? So don't expect your spectrum to be exact. It's an approximation, and I will show you exactly what is the magnitude of corrections that we already know that this induces on the spectrum. The other approximation that you can consider is, okay, so let's assume that my particle will receive a high momentum kick of one single interaction. So we have the opposite limit, in which we have few hard scatterings each one where we have a large momentum transfer. The potential is usually characterized by being already broad. And this is a situation in which the interactions are kind of rare. So the picture that you have is basically this one. So the medium is kind of dilute, but it's very effective to kind of kick your particle. So this is what is usually called the opacity expansion, and amounts to save exactly, but at fixed orders of your fields. Okay? So instead of resumming and just cut on the two endpoint correlation functions, you solve this exactly, but just in a given order of fields. So, which allows you to exactly solve also the path integral. So this will, of course, will describe very accurately your spectrum of gluon radiation if this gluon has a very large momentum transfer, okay? But it will fail in the rest of the spectrum. That's the price to pay. This one, of course, is always an approximation, so don't expect to be exact, but it captures the qualitative features of your spectrum. Okay, so perhaps before I can go ahead in showing you exactly how the Q-hat actually arrives from here, okay? From here afterwards is just to show you how this puts together in a calculation and finally show you the results of the spectrum that I have there. But I suggest that we make now a quick break, okay? 10 minutes, and we will restart soon. Okay, so let's go back to the problem that we were trying to address. As mentioned, I will just focus on this approximation, okay? But for records, there's also this one. And if I now want to expand in around R and just cut the first non-trivial term, I need to expand this this exponential. And this means that the thing I now want to calculate is just given by, this would be more or less the first term that survives, right? Because I have 1 minus this, so let me put actually like this. This would be the first term, the one that is linear in R. But of course that from here, what you get is something that has the potential and linear in momentum. Now, because we are considering the medium to be isotropic, okay, and again, this is valid for central-central collisions. There are people that are actually working beyond this. But if you go for these isotropic considerations, then of course that the potential is just dependent on exactly the total distance. It's not sensitive to the direction. And so you have an odd times an even function. And so this correction is, or this first term, is actually 0, just because we are considering an isotropic medium. So the first the first non-trivial correction, or the first non-trivial term, is actually the quadratic one. And so this means that I can approximate the dipole cross-section as 1/2 the Fourier transform of your potential times the momentum square. And now I will need to average, okay? And already from here, you can see that you will gain an extra factor of 1/2 because I have here the cosine between the two vectors. And because it's this 1/2, this means that my dipole cross-section in this case is just quadratic in energy, in distance times something, okay? That's for the purpose of our variables is actually a constant. Yes, you will have the details here, but for a given potential, that is going to be a constant. And this is exactly what we call the dipole or the harmonic oscillator approximation. Yeah. Yeah. So there's a problem here because you need to ensure that, so this is actually why we move from full Yukawa considerations into hard thermal loops, because that can give you a sizable contribution for this. Yes. So there's still a lot of discussion exactly how to put this, for instance, into more robust definition of what is the jet transport coefficient, because it is highly bounded for that lower threshold. Yes. Okay, if I now reinsert this into my dipole object, I have now just a very easy thing to integrate. And to make it even more simple, I will just consider a density that is constant. Okay. Again, extrapolations beyond the static density can also be easily accommodated. So all these are actually things that we now already know how to do. I'm just simplifying here for the simple, to keep arguments simple. So this means that the constant is density. What I have is basically the full length of the medium that the particle will cross times exactly this constant and this r square. And let me reorganize this a little bit. R square L, and here what remains is 2CF and C. And this is exactly what we call the Q hat. Why we call this the Q hat? Let me give you give me just a couple of minutes. So again, the definition of Q hat is N CF K over 2 pi square, and the second moment of your Fourier transform of your potential. That's the definition of Q hat. Okay. And by the way, Andrea, here is a definition of the color factor. So now it depends, exactly, now it depends on how you define exactly your Q hat. You can define regardless of the color factor, and this would be a prefactor that you have. Usually what people list in the papers is actually the fundamental Q hat in the fundamental representation, because they are considering the quark as the baseline. At least for single particle measurements. For jets, for instance, I believe that some of the things that we are presented are actually for Q hat without the color factor. So of course, this will create a shift in the average value that you get. Okay, so this means that your dipole that now let me put explicitly that will also depend on the medium length that you cross is simply given by a quadratic term in the distance. One of the objects that we just discussed was the broadening, right? And now if I want to put this into the broadening, which is basically the Fourier transform of this object, you will now get exactly, so let me just put this more explicit. It's easy for you to identify what this distribution is? The Gaussian. With an average value that is given by Q hat L. That's where the definition of the Q hat, that's the one that we introduced yesterday, as just being the average momentum that a particle acquires per mean free path, comes exactly from this. Okay? So here it's easy to see that this is a Gaussian with a width characterized by Q hat L. Okay? So we finally closed the loop to show you why we are so always obsessed with this Q hat, with this Q hat parameter. Okay, so yes, it's the average momentum that you acquire per mean free path, but is actually the Gaussian distribution that appears from the second moment of your dipole. So if you want to stick with the more formal definition, that's exactly the definition of Q hat. Okay, and don't forget that, as I was mentioning, this color factor here will be one of your definitions of the Q hat. So when you see listed expressions from Q hat, just make sure which kind of color representation they are implicitly or not including in the definition of Q hat. Okay. By the way, it's also possible to see that this distribution of the broadening again satisfies a diffusion equation. In momentum space. Okay, but this I will leave. I think Soren will talk a little bit more about this. Okay. So finally, we close the loop on what is exactly what is the physical meaning of the jet transport coefficient, how it arises. We already identified the propagators, and we already identify what kind of structures we need to compute when we want to evaluate the equivalent of the cross-section. Now it's time for finally close the loop and write the full amplitude and go into the cross-section. Now, as you can imagine, this is kind of a long process. So what I did here was basically to give you the building blocks that will enter this calculation and kind of how we get the final result by using this kind of medium averages, okay? So from here onwards, let me be a little bit more schematic on what kinds of objects we need to compute. So to recall, what we want to calculate is exactly this process. And here is just, the box represents the multiple interactions that we have all across our diagram. From here, we obtain the matrix element. And what we want is exactly the square to get the single gluon energy spectrum, which is the equivalent of the probability of emission that we define in lecture 1 in vacuum. Remember that in vacuum, this is just alpha s, 1 over s, 1 over z, 1 over theta, double differential in angle and in the fraction of energy, and you, of course, have freedom to choose whatever collection of kinematic variables that you want, okay? And this is exactly what we want now to compare to. Okay, so to do this discussion, first of all, our matrix element will have something in which there is an emission at a given x, at a given longitudinal position, right? So this is the first key difference with respect to the vacuum, is that the radiation in this case is a longitudinal or a time-integrated process. In addition, we have the propagators. So this means that now my matrix element for the contribution that has a gluon will be 0 to L. And now what I will have is the propagator of the quark that goes from L plus to X plus. This is L. This is, in this case, 0. I will have also the gluon propagator that now I will assign instead of a green function, instead of a Wilson line, a green function, because don't forget that the gluon will carry, in principle, a small fraction of energy. So this means that the Wilson line will not be applicable anymore. We need to account for the first aconal correction, at least for this particle. We'll have some sort of vertex structure. And we'll have the final Wilson line that characterizes the quark before the emission. Okay? This will be basically the structure for your matrix element. The only thing that we didn't explicitly define was the vertex. Now, for the vertex, what we have is basically this thing. Right? And as you can see on that expression, what we have is this, this, and this. Right? So the only thing missing is actually this process, the particular vertex itself. And so because we are working in high energies, okay, and we use exactly the light cone gauge, the minimal structure that you will have here is actually very similar to what you obtain already for the vacuum. If you go and check exactly what is the structure of the matrix elements during the lecture one, we found, okay, you actually found two terms because we were considering the quark and the anti-quark in a QQ bar antenna setup. But the term that goes, the kinematics that where the gluon lives is actually something like this, that we define exactly as a current times the polarization. And so in the medium, we can simply connect the momentum space now to the coordinate space, because our propagators don't live in a momentum space. They live in the coordinate space. Such that the structure that is there for the vertex will be proportional to 1 over k plus and the derivative, because don't forget that we have here also the exponentials that come from exactly the energy momentum conservation. And we have these exponentials also in our definition of the propagators. And so our M, just for the part of the vertex, will have something that looks like this. Okay. So this is kind of a more heuristic discussion. You could do exactly this, all this calculation carefully, and you would arrive to this result. But the key thing is that within these limitations that we are considering, the vertex itself is not exactly modified by the scattering. What is modified is exactly the propagation. Okay? Of course, overall, you will get an effective effect on the vertex because you are considering, of course, some modifications since the production of the vertex until the medium length. Okay? But on this vertex itself, there's no modification. Okay? So you emit a gluon with a given transverse momentum, just as in vacuum, but of course that afterwards it will start to broaden within the medium because the medium will basically increase or decrease, but in any case it will shift the initial transverse momentum of the gluon. And that's why you make this transition for coordinate space, and now all this information is like an internal momentum that you don't know what would be, but in any case, you see the effect through this operation. Okay? So don't forget that that object will basically propagate all the modifications and all the effects of the emission up to the end. So we don't explicitly modify the vertex, but of course the final consequences are there nonetheless. Question? No. So this will be your amplitudes. And now for the spectrum, what you will have is the integration over the emission in the amplitude, in the emission of the conjugate amplitude, and the matrix elements that you already know more or less what is the structure. And so from here, what you are exactly doing, and now I can plot this more carefully, is exactly this. M dagger. And as I told you, the averages now are performed across these different regions and are carried out independently. So in the end, you have to basically calculate objects as this one, and this one. And of course, if you want to now include, for instance, Brownian motion in all particles and just consider green functions all over, you can do it. Okay? Of course, here it starts to be a little bit more technical because now you don't have so trivially 2-point functions. You have 4-point functions. Okay? And the result, again, is not trivial. It's possible, not easy. Okay? And each of these sections will contribute also physically to these different objects, and you'll get, again, the interpretation of the broadening that we were looking at. So here you would have the broadening of the quark. Here you would have the emission kernel. Because don't forget that despite we are at the very element discarding the effects of the medium, there is a formation time associated with this gluon, right? Under which there will be an effect of the medium. So the medium will affect exactly the formation of these gluons, as we already also saw yesterday. Of the gluon, and this one corresponds basically of the broadening of the final system. So in each of these sections, we consider basically the system to behave as a dipole whose survival probability at each one of these steps will depend on Q hat. Okay? And of course, if you now want to consider the evolution of the medium, you can basically plug in the density and account exactly for this. Questions? Okay. Yeah. No. Not at all. The is so here it's actually a little bit more difficult because you also have to account for the interferences with the vacuum. However, one of the things is that let me already show exactly the results because I think it's easier probably. So one of the things that will happen to your spectrum is that it will no longer have the divergences that we found for the vacuum. Because in vacuum, yes, there is no, let's say, medium, but here there's always a medium that provides the minimum quanta for your emission. So you'll no longer, exactly, there is a scale. And so this is basically the result of this calculation, okay, in the harmonic approximation. And as you can see here, okay, this is the information that still has the transverse momentum information. and there is no collinear singularity. Okay, so the medium screens, and there is some sort of broad distribution, which was exactly the arguments that we already understood from the formation time arguments, right? We saw that the typical scale, the typical angle at which the radiation is emitted is actually large angle. Large angle means that I don't have a collinear distribution, I have something that is broad, okay? For the energy spectrum, let me just recall exactly what we derived. Yeah. So if you this is what we derived for the medium. So this is the medium spectrum. And this is what we call the BDMPS spectrum, which basically gave for the persons that first derived exactly this this kind of process. And they used the harmonic oscillator. So that's why we use this thing. And so this means that, let me put here in the same structure that we saw for the medium, this one. And now if we compare to the vacuum one, this actually goes as alpha s log of q squared over k perp min, because don't forget that we have exactly the divergence. And this comes from the fact that your emission probability was d omega over omega d theta squared over theta squared. Okay, I just integrated out the isolated the energy. Okay. So the first thing is, yes, in vacuum there is no scales associated with the radiation. Okay, so it's pure kinematics. But in the medium now you have a scale dependence. So this is the first effect. The other effect is exactly the loss of collinear structure. And finally, on the energy, if you now look for the green line there, this corresponds exactly to this scaling that you see here. 1 over square root of omega c, because it's normalized to the energy. Okay? That is the green line. And as you can see, people usually depict this as a function of the medium scales, which is the Q hat L, which was the saturation scale, also used in color glass condensate formalisms, and the characteristic radiation, which is Q hat L squared. The factor 1/2 comes from, if you consider light cone gauge with factors 2 only for the plus components, or square root of 2 as we did it here. Here, yesterday in the lectures, we just considered Q hat L squared as being the scaling. However, as soon as you include finite medium corrections, you have now a suppression of the spectrum, okay? So that scaling of BDMPS is actually valid in this particular region. So when we go for very small energy, you would assume, wait, but this, if I recall the formation time argument, we saw the formation time goes with the energy, right? So if the energy goes to 0, the formation time is instantaneous. But don't forget that at that point, you hit the Bethe-Heitler regime, in which this scaling is no longer true. Okay? For the Bethe-Heitler regime, we saw that the spectrum actually goes with the L. It doesn't go no longer with the formation time. So you have the information of the mean free path, and that's exactly the responsible for dropping the medium, the spectrum. On the other side, of course, this decay, this longer decay, should happen always, not only because of the parametric shape, of the spectrum of the BDMPS, but also because at some point your formation time is going to be so large that will go beyond the limits of the quark-gluon plasma. So the quark-gluon plasma cannot contribute for this emission, okay? And that's why the spectrum should nonetheless goes to 0 for high energy. Don't forget that here we are just analyzing the medium contribution of your radiation. If you see the total radiation, of course, it amounts to have this term plus the vacuum contribution nonetheless. And this will be the total spectrum that you actually see, okay? Here is just a medium. Of course, it has the interferences of finite length corrections, which you could also consider here. You just need to also consider the interferences when the emission happens outside of the vacuum, and etc. Okay, all this will be will change a little bit the picture that we see here, but nonetheless. Mm-hmm. Sorry?
What does the harmonic oscillator approximation do there? What is the physical meaning of that? What are you approximating?
The harmonic oscillator is approximating the dipole that you consider. So in the 2-point correlation functions, you are considering that these particles will be kind of nearby. So physically, this means that you are considering a very dense medium in which you go multiple scatterings with it, but the amount of energy that you exchange with the medium is very small. Okay? Okay. So for that particular energy spectrum, you actually can consider this as this one is the LPM region in which your spectrum goes as 1 over omega, or the square root of omega. And this was when we kind of considering the formation time to be larger or of the order of the mean free path. Here you have a suppression. And this, of course, comes also from the fact that your formation time at some point will be larger than the medium scale. So it is suppressed. And this is the Betz-Leitler regime in which your formation time is now bounded for the mean free path, okay, which is the incoherent limit. This is more or less our understanding of that spectrum using just the scalings that we discussed yesterday. And just to final, I mentioned you, well, this is the harmonic oscillator approximation, right? This is not exactly the full result. The full result is illustrated more or less here in solid lines. The dashed ones are the ones from the harmonic oscillator approximation. And as you can see, yes, it's not the same, but all the qualitative features more or less appear there. Okay? If you decided to opt instead for the opacity approximation, what you would have is a perfect characterization of these tails here. So the harmonic approximation, the dipole approximation or harmonic oscillator approximation, what it gives is that it underestimates the contributions from these large kicks, which we never considered in the first place, because we are always assuming that the dipole distance is small, and this means that we will only be able to receive small momentum. Okay? And that's the limitations of the harmonic oscillator approximation. Nonetheless, all the characteristics are more or less there. Now, it's a question of precision physics, yes. And this basically amounts to introduce all the corrections that we have been discussing, right? Longitudinal corrections, higher endpoint functions, because we are limit ourselves to just 2-point correlation functions, introducing evolution effects in the density, considering interferences also between pre-QGP and QGP phase, which is still very under debate, and also to consider, for instance, these anisotropic cases of the medium to account exactly for flow effects that comes from non-central collisions. And of course, these non-isotropic can also accommodate other sort of fluctuations that we might hope to kind of see from the quark-gluon plasma itself. Questions? Yes. This is for Yukawa. So, but you could consider also some other term potentials. So in this case, we did it for the Yukawa and for the hard thermal loop. But in any case, the level of corrections of the harmonic oscillator to the full solution is more or less the same. The shape of the spectrum, especially this low momentum part, changes a bit, because this is the one that is most sensitive to the shape of your potential. Okay. In the energy spectrum, it's less visible because you integrate out this information. So. Sorry? This one here? So, for small case, because there is, so in the full solution, we actually don't have a Q head because we work with the full potential of Yukawa. So you have to make this connection between the Q head and your potential, and this is not exactly straightforward. So we just use more or less of a prescription to have a qualitative comparison. So it's difficult to have actually an accurate comparison between using the full solution and the harmonic oscillator because you integrate out this in the definition of Q hat, but you actually have a divergence there in the infrared that you have to be careful. Okay. More questions? Okay, so if not, Friday, we will address basically the problem. So we understand what the medium does in terms of formal, our formal calculation of the single gluon emission. We understand what this diffusion does on the emission spectrum, how it changes on the single gluon case compared to the vacuum. But in the first lecture, I always told you a jet is not a particle, right? So in order for us to understand exactly what are the effects on our jets, we need to move beyond a single emission, okay? So the next lecture will be to cover exactly how this diffusion will affect now when we have multiple possible emitters within the medium, okay? So this will be on Friday. Thank you very much.